Yeah, hi Cassie. All right, so the next topic we're going to look at is chemical bonding and how bonding works. All right? Not that bond, the other kind. All right? This kind of bond. So what I actually have here is a molecule of chocolate. Well, the main active ingredient in chocolate, okay? That's the kind of ingredient that makes you feel happy when you eat it. All right? This is what triggers your dopamine pathway in your brain. And the only reason why it triggers that happiness is because it's bonded in a specific way. If you can manipulate the bonding of elements, you can change their form, function, and physical properties. All right? So here I've got this is a type of amine-based benzyl ring. It's a hydrocarbon. There's a ketone there. All right? Actually, that looks like more of an amide link. And then what do we got here? An tertiary amine. All right, you won't need to know any of that yet. That comes later. That's year 12 stuff. But just be aware that when you arrange atoms, specific bonds will affect how they interact with other molecules and yourselves and the universe. So this is just going to be a brief introduction into the kinds of bonding we'll be looking at. And we're going to examine 3 different types, and the third type has 2 subcategories. So there are going to be 3 different types of chemical bonds. The first we'll look at is metallic. Put that there. All right. Metallic occurs obviously between the metals, and only between the metals. Metals between metal atoms of the same type or metal atoms of different types. Which, if there's 2 different metals, we call that an alloy. All right, steel is an alloy. Titanium, quite often it will be in an alloy form. All right, but if you've got just elemental metal, we'll look at that kind of bonding as well. The elemental iron, for example, zinc, and magnesium. When we look at metal bonding, it will involve the positive metal ions, all right, being arranged in a 3D lattice. Now, what does that mean, a lattice? Well, all it means is a repeating pattern, okay, evenly distributed repeating pattern, kind of like this, where they're spaced out evenly, all right, and that's how metals are arranged. That's how metal atoms arrange themselves when they're bonded together. They have all their positive guys rearranged, and flowing through them is a cloud of electrons. It doesn't really want to attach to anything because remember, metals have low electronegativity. They can't hold those electrons very well, so the electrons just dance around all the others in a 3D arranged lattice. All right, so we'll look at the properties of metals and why that cloud actually makes them very useful, because that cloud makes them pretty durable. You can bend them and you can pass electricity through them. All right? The outer electrons are free to move, and that is vitally important when we look at metallic bonding. We will also look at ionic. Okay, we've covered a bit of ions, but we'll look at that more in depth and more three-dimensionally. Okay? This occurs between metal and non-metal atoms. For example, sodium chloride, magnesium oxide, anytime you've got something considered a metal and a non-metal coming together, the non-metal, being high in electronegativity, there's that word again, will pull the electron away, making itself negatively charged and leaving the metal positively charged. And once those charges are in place, then they get attracted, all right? Opposite charges attract. All right, so it involves the metal atom giving an electron to the non-metal atom. This is done so that they both have that full outer orbital, the full outer shell, as we know. And as we also know, the noble gases will not be involved in that sort of situation, all right? Because they already have that full outer shell. And the 3D lattice looks something like this. You arrange evenly the positive and negative particles, all right? This is if we really zoomed in far on sodium chloride, this is what we'd expect to see. No, that wouldn't be that color. Artistic license. Okay. The other we're going to look at are covalent, which occurs between two or more non-metal atoms. All right, involves non-metal atoms sharing those electrons. Both want them as much as the other, and that creates a bond. All right, and they both share to fill that outer shell. And there are two subgroups of covalent bonding. Valent, meaning valence, outer shell. Okay. The first is molecular. That's when you have a small number of atoms in little discrete units, which we call molecules. Examples include hydrochloric acid, nitrous oxide, water, carbon dioxide, oxygen, anything where there's discrete, like usually less than 4 elements in that molecule, all right? Little discrete particles. And the last one I just want to introduce to you will be the continuous covalent, all right, or the covalent network or the covalent lattice. It has a few names. All that is that you have all these elements, these non-metals sharing electrons, forming really strong bonds, and it's just repeated units of that happening. And this gives giant lattices forming, or what we call polymers, poly meaning lots, containing millions of repeating units. And the most classic example and the hardest example, the strongest example, is, of course, diamond, which is the hardest substance on this earth. Graphite is another example in your lead pencil. It's not a lead pencil, it's technically a graphite pencil. We'll look at why that is and how it gets on the page. Rocks, silica dioxide, silicon-based repeating units of elements bonded together covalently. So these words you'll get familiar with. If you want to look them up now, go ahead. I mean, really, get ahead of it and have a look at the definitions if you can. Google it. Get familiar. Plastics will also form a long chain of covalently bonded molecules. The table here is actually plastic, all right? It's hard because there's a long chain of molecules just sharing electrons and holding together. They're all going to be holding hands, and that gives them great strength and very high melting points. So those are the types of bonds we're going to go into, and we're going to go a bit more in depth with ionic and the properties of metals. I'll leave that there. Something for you to process, and that is our heading for the next few weeks. Thank you all.